All right, so now let's briefly recall the EM algorithm, and then we're going to apply it to this problem of hidden variable estimation, which we mentioned before. Right, so so let's say we begin. Okay, so maybe let's draw a picture here. Right, you have a data manifold, right, and then you have some model space, right? So the model space is given by probability distributions, which depend on the observable y, the hidden variable h, and then parametrically depends on this c. So c is a coordinate, if you will. It's like on M, right? And then we have the data manifold, which, if you recall, it's like has the form of this sort of conditional expectation in the observable variables, which comes from the data you've sampled times this unknown conditional probability, right? And that sort of that gives you a joint probability distribution on both the observable as well as the hidden variables. Okay. All right. So I'm going to start with a point on the on the model manifold. So this is the space of models, and then this is the space of data. Right. So so we start with C0, right, as an initial parameter. All right. So let's see C0. And then what you first do is what's called E projection onto the data manifold of that point. And then once you've done that, you can do a second step, which is M projection back onto the model space. And the idea, of course, is to sort of go keep iterating between E projection onto the data manifold and M projection onto the model manifold, and eventually it's like you'll get, well, if the method converges, it's like you'll get to a pair of points. It's like on the data manifold and the model manifold, which is the is pair points which minimize the KL divergence between those two submanifolds. Okay. All right. So, So you start with this as an initial parameter, and we apply E projection to D, right, to obtain the conditional probability. Let's see. So QH condition on Y is PH condition on Y, and then parametrically dependent on E0. So this determines a candidate for the observed distribution in D, right? So this gives a candidate for the observed distribution. In D, right? And then once you've done that, it's like you want to find a new candidate. It's like in the model space, right? So we can compute the log likelihood to evaluate the likelihood of a new candidate. C in M. All right, so L cos C 0, right, is equal to 1 over n, the sum over I of the integral of P conditioned, of H conditioned on yi cos C0 log P yi H C dH. And we do this for observed data. Y1 to Yn. Okay, so this is the all right. So I should say the following, right? So you have to compute this conditional probability, and once you have the conditional probability, you know this QH conditioned on Y. And if you know QH conditioned on Y, then you know the point on D, right? So that's giving you this E projection step, okay? So, right, yeah, so anyway, so that gives you this candidate. And then once you have that, it's like you want to find a new candidate point, because C, it's like on M, all right? And this is, what you do is you evaluate this log likelihood, and, you know, you want to, basically maximize this, right? So we maximize this over cos C, right? And this gives the M projection of the point in D, right, to M. Okay. All right. So then it's like, so that's basically one cycle of this EM algorithm, right? So in principle, given something in the model space, I can compute this conditional probability, right, by, yeah, I can compute a conditional probability, and then from that, it's like I know what this QH condition on Y is. It's like, and that gives me a point that's like on the data manifold. And then it's like, in order to project using M projection back onto the model space, I maximize this log likelihood function, right, over the point cos C, right, and then the cycle repeats itself. So the theorem is as follows, that the KL divergence decreases monotonically by repeating the E step and M step. So hence the algorithm converges. So it should be observed that this M projection is not necessarily unique. So remark, the M projection is not necessarily unique. Unless M is E flat. So you could end up, it could converge, it's like it could converge to a local minimizer. So it can converge to a local minimizer. All right. Okay. So that's sort of briefly this EM algorithm, and then the next thing we're going to, well, actually, let me go ahead and do that. Is to look at the example of Gaussian mixtures. Okay, so we looked at this simple example. It's like of Gaussian mixtures where you had weights and you had means. It's like, but the variances was normalized. Okay, so let's look at that simple case, right? So the parameters to be estimated are the weights W1 to WK and the means mu1 to mu k. So if you recall, what had happened was that we had thought of specifically which Gaussian you were taking a particular sample from as being a hidden variable, right? So that's how we had formulated the Gaussian mixture problem as an estimation problem with hidden variables. Okay. So, so we begin. I should say what Cc is. So Cc is just Wi and mu I. Right, I equals 1 to k. So given an initial C0, right, you let C L right, which is W L I mu L I, right, be a candidate at step L, right? So so we need to do this E projection step, right? So we E project P, which Y and H conditioned on, well, not conditioned, but sort of parametrically dependent on CL to D to obtain QL H conditioned on Y. Okay, and then this QL H conditioned on Y then parametrically dependent on CL, right, is equal to W H L. So if you recall, the hidden variable is which of the distributions, which of the k distributions you're actually sampling from. So that's where this WHL is, right? So H is integer random variable, which varies from 1 to k, right? So just a reminder. So 2 pi p y CL exponential of minus 1/2 y minus mu L H squared. Right, so that's the conditional probability. Right, and then the conditional expectation. Is L CL equals the sum over H of PH conditioned on Y with this unknown, well, sorry, with the previous point, right, with the candidate, times log of WH minus 1/2 Y minus YH squared. I'm summing this over H, right? And this is up to some constant which doesn't depend on the parameters, right? So if you recall, it's like when we were computing, it's like the KL divergence, it's like in this sort of more general setting, there were some terms, it's like, which, you know, it's like depended, for example, on the Q bar Y, right? But it didn't depend on essentially which point in D it's like you were, or which point in M you were, okay? And so those are what the constants we're referring to. It's like they don't depend on the things which you are trying to vary in order to achieve this pair of points in D and M, it's like which minimize the divergence. Okay. So, all right. So this is the this is the you know, it's like E projection step. It's like, and then in order to do the, okay, so computing this conditional probability, right, this conditional distribution, right, is what allows you to find this D point, this point in D which you want, right? And then what you want to do once you have that is to do M projection back onto the model submanifold. And then what you have to do there is you have to maximize this conditional, I mean this sort of log likelihood term. So the way you do this obviously is that you differentiate it and then you make it equal to 0. Okay, so so to maximize this, right, differentiate and set it to 0. So that gives me the condition that WL plus 1H is equal to 1 over N, the sum of PH conditioned on YI, okay, and that mu L plus 1H is equal to the sum over I of YI PH conditioned on YI cos CL over sum over I of PH conditioned on YI focus CL as well. Okay. All right. So anyway, so that's the EM algorithm applied to this estimation problem. It's like for Gaussian mixtures, right? And again, this is the E projection step. It's like where you have to compute. It's like this conditional probability in order to figure out it's like what point on D it's like you should project to using E projection, and then it's like to go from D back to M. It's like you have to maximize. It's like this log likelihood estimator, right? This log likelihood, and you do that by differentiating in respect to the variable, and then setting it equal to 0, which gives you these updates. All right, so let me just stop here. Thank you.